In graph 14.2, we illustrated what lies behind a competitive equilibrium in an output market, where many consumers and producers are coordinated by the equilibrium price that emerges. The same can be done for the labor market, where the equilibrium wage rate coordinates workers and producers. We'll begin in panel A with a single producer J and the production choice set that this producer faces. Taking the output price P as given, there exists some wage rate W prime such that the highest possible isoprofit that the producer can reach intersects the origin and therefore results in zero profit. That's the lowest wage rate at which this producer will hire any workers. As the wage rate falls, the isoprofits will become shallower, and the optimal production plans will therefore include a larger number of workers than they do at the wage W prime. As we first showed in chapter 11, we can illustrate the same thing using the marginal revenue product curve that's derived from the shape of the production frontier. In our case, since the production frontier has initially increasing marginal product and eventually diminishing marginal product, the marginal revenue product curve will be initially upward sloping, but eventually downward sloping. At the wage W prime, the firm will hire the number of workers indicated in the upper graph. As the wage falls to W star, the number of workers hired by the firm will increase. The firm will hire no workers above the wage W prime and will hire workers along the marginal revenue product curve for wages below W prime. This gives us the darkened labor demand curve for firm J. Since there are many producers in a competitive market, there'll be many such individual demand curves that we have to add up to get to the market demand curve for labor. To build the supply side of this market, we begin with a single worker I, and we assume that the initial wage rate is W, forming the green budget constraint over leisure and consumption. The worker then optimizes at bundle A, implying leisure consumption LA. If the wage increases to W star, the worker faces a new budget constraint and now optimizes at bundle B. And if the wage increases further to W prime, the worker optimizes at bundle C. From this, we can derive the worker's leisure demand curve, the demand curve that tells us for any wage rate how much leisure this worker will consume. The more leisure the worker consumes, the less labor the worker supplies to the market. The amount of labor that's supplied is simply the time endowment that the worker has minus the leisure consumption he consumes. We can therefore derive from the leisure demand curve the worker's labor supply curve, which in our case takes on the backward bending shape that we discussed in chapter 9. We then add up all these individual labor supply curves for individual workers to get the market supply curve for labor. That will intersect with the market demand curve for labor to give us the equilibrium wage W star. That wage in turn sends a signal to producers telling them how many workers to hire, and a signal to workers telling them how many hours of labor to supply. Just as the equilibrium output price in graph 14.2 coordinates producers and consumers, so the equilibrium wage rate in this graph coordinates workers and producers. It coordinates them in a way where the quantity of labor demanded is equal to the quantity of labor supplied. But no one actually is aware of this coordination. Everyone simply takes the price signal, in this case the equilibrium wage, as given, and does the best that he or she can given her circumstances.